All right, I got a couple of videos to make this morning, get through our day. This first one is about springs. Part of what we're doing with the simple harmonic motion chapter is we're doing the mass and spring system, and occasionally springs are combined. And there's two main ways to combine springs. One of them is in parallel. Springs in parallel are, as the name suggests, right next to each other, but it's more important that they share, and I'm just going to do two. I'm going to hang a big old weight from these springs, and that weight is going to pull the springs downward. Now, this spring is going to have a spring constant K1. This spring is going to have a spring constant K2. And in order to understand what's going on here, we need to figure out what's going on. So now each of these springs will have the same amount of stretch when this mass goes down. If it goes down a distance x, both of these springs are going to get stretched by the same distance. Excuse me. Wow. I was trying to say the word difference as well. They are going to have different spring constants because K1 and K2 are not guaranteed to be the same. Now the question is, what about the other ingredient in the force law, the force? Will they have the same force? And the answer is no. They may have different forces. However, the total force must be the sum of the force on spring 1 plus the force on spring 2. So we have the same x, so we don't have to use a subscript with x. We have different spin constants, but they're labeled K1 and K2, and we have this relationship. So this is the total relationship. Let's figure out what these ingredients are. Well, ingredient number one is that the total force is going to be due to an effective spring constant. In other words, pretending that these two springs are one spring of another number designation, another number characterization. Then we can also say that F1 is K1 times X and F2 is K2 times X. Again, all the X's do not have a subscript because it's all the same number. So we can now use this statement here and we can put in our information. So K effective times the stretch is going to be K1 times the stretch plus K2 times the stretch. And the stretch cancels out, leading us to the result that the effective spring constant for springs in parallel is simply the sum of the two spring constants. Two springs in parallel act like a spring that is stiffer or larger spring constant by just kind of adding their spring constants. Now, you can identify whether things are in parallel or not by the fact that they have the same amount of stretch. That is the defining characteristic, not the geometric parallelness. I have seen springs used in a very interesting way. For example, in automobiles, sometimes you got a situation where here's the bed of your truck, and there is a leaf spring that goes down like this, and the axle sits here, and the axle is the thing that's providing the force, but in between the axle and the bed of the truck is another spring called a helper spring, and it might be a coil spring or even just a rubber block. And what happens is you can tell that these two springs are in parallel even though they don't look like this, because when that axle goes up, it compresses both springs the same amount. Okay, what's the other option, you might say? Well, let me write over here. This is parallel springs. The other option is to put your springs in series. And much like in the case of resistors in a circuit, series means one after the other. So in this case, they might have different stretches. That's right. If this spring up here was a very loose spring, a very wispy spring, and this one was a very strong spring, then most of the stretching would be done by the upper spring. They, of course, will have different spring constants, but what they will have is they will have the same force throughout. Much in the same way that a rope transmits force with the same force throughout the rope, transmitting the force into the support, springs do the same thing. So let's see what we can figure out. Oh, they will have different stretches, but the total stretch will be equal to the stretch of one plus the stretch of the other. So that's going to be our starting point. And now we can go over here and we can write what's true. What's true is that the total amount of force is going to be due to some sort of, okay, Harmon, you've just screwed up. the total amount of force, which is, they're all the same force, so we can just use F, equals an effective spring constant, this needs to be a lowercase k, times the total amount of stretch. And the force on spring 1 will be the constant from spring 1. Oh, again, we don't need the subscript, times the stretch of spring 1, and the force on spring 2 will be constant 2 times the stretch of spring 2. Now, this is a little more difficult to deal with. What we have to do here, and please, hold on a sec. I've got it. It's in here somewhere. That is not good whiteout. Oh well, you can tell I don't use whiteout very often. Okay, so what we're going to do is we're going to monkey each of these around so that x total is going to be F over K effective. So x total becomes F over K effective, and that x1 becomes F over K1, and x2 becomes F over K2. And the F's cancel out, leaving us with this 1 over the effective spring constant equals 1 over spring constant 1 plus 1 over spring constant 2. And this is the rule if you are in series. Again, series springs will have the same force. There will only be one line of them. Write series up here. And they use a reciprocal rule. A lot of people don't like this because you have to reciprocate the two spring constants, add them together, then you have to reciprocate that answer to get what the effective spring constant is, and then you just pretend that the total force is the effective spring constant, however you calculate it, times the stretch. Okay, that is how to handle springs in parallel and series. For those of you who took physics before and you know about resistors, you may notice that the parallel rule for springs is the same as the series rule for resistors, and the series rule for springs is the same as the parallel rule for resistors. And there's an easy way to justify that. That is to say that springs store energy and resistors dissipate energy, so they operate in reverse. Also, there is a circuit element that stores energy called a capacitor, and capacitors combine in parallel with this rule and in series with this rule. So capacitors are to circuits what springs are to mechanical systems. All right, that's a quickie for today, and we'll move on.